For today's quiz, we've got this thrust bearing, and we're doing a series on how to do long-term projects with students and teachers. And we noticed that as this thrust bearing moves, it tends to jiggle a little bit, especially when we have less balls in that bearing. So what I mean by jiggle is you can see that it kind of sways. Hopefully you can see that jiggle. Our question for today simply asks, what would happen if I took those spheres or those balls in the bearing and reduced their size or made them way bigger? We simply want to know about its stability. So here's what your quiz looks like today. Let me hold that up. As always, mark your answer as completely as possible and list your level of confidence. Typical student responses on this quiz is, I don't know. Most of our quizzes, they have a really strong intuition one way or the other, but not on this quiz. And that's what makes this one such a great long-term project. They just don't have the tools. They don't have the experience to know anything one way or the other, and it's not perfectly obvious. It's also the reason why it makes a good long-term, because a lot of people will say, you know, AI can give us anything. I don't know if AI could answer this question. I don't even know how you'd ask AI this question. So, typical student responses, I don't know, but if I had to go with one, it seems like the larger the ball, the easier it is to get things to roll, so maybe it would be the larger ball would be less stable. If you like what we're doing here at the Idealized Science Institute, please subscribe, like, and comment below. Okay, here's what we're going to do. We're going to give this whole table a nice big jiggle. We're just going to do this visually at first. Some of you are at work, probably sneaking a video. You need to get back to it. We're going to give you the answer quickly. And then, those of you that stick around, we're going to continue doing this long-term project. All right, let's just start with our base bearing here. And if I were to give this a little bit of a jiggle, the whole table, like an earthquake jiggle, you can see it moves quite a bit. Now, if I replace those three with an even smaller set, put these down, and I'll try to keep them lined up. I'll put two over here, one over here, and like a triangle. Now I'll give that a jiggle. And you can see that one really wiggles a lot, probably more than we had before. Let me just go back and put the original bearings in the same configuration. 1, 2, and then I'll have 3 here, like so. Put them like this. And now I'll give table a jiggle. Not as much. So the really small bearing jiggled the most so far. Let's go one size up. So I'll get rid of these monsters. I've got a whole set of box of different size bearings. I'll put the next size up. And now I'll give that a jiggle. Nothing, almost nothing at all. Let me go one size up from that. Put these two in, like this. Give a little earthquake here. Again, very stable. Put these monstrous spheres on here. It's actually hard to get them onto the race. And if I were to give this a jiggle, oh, there is some movement. It almost seems like we're losing stability here. So it appears that the size of the ball is going to depend on how well it fits into this groove. So does not seem like the very small ones have great stability, and the very large ones also have problems somewhere in the middle. It seems like you need the appropriate fit. All right, that's your quiz, but we're going to go into a much deeper dive if you stick around. All right, let's start diving into this a little bit more systematically. Look, we have 1, 2, 3, 4, 5 different size spheres here for the balls and the ball bearings. Let's use a measurement tool, and instead of saying this one's large or monstrous and this one's really small, let's actually get measurements. Probably the best tool for this right now is going to be a vernier caliper. Cheap, most classrooms have them. If not, you can go to one of these tool stores and buy them for $1 $2, something like that. Now, a micrometer would even be better, but most schools don't have that. Most students don't have it. Harder to read. They're better, but this will do just fine. All right, so I'm going to end up taking each one of these. Now, I'll take this first one right here, and you want to, look, whenever you're taking the measurement, I'm right-handed, I'm going to put this on the longest part right in the jaws. I'm going to crimp this so it doesn't move, and then I can look where that 0 is up top, and it's pretty close to 2 inch. Let's call that our 2 inch. It won't matter if we're off the slightest bit. In general, we would say that's a 2 inch ball. This one here is going to end up being roughly a 1 inch, and hopefully we can see that. And then our next one down, this guy would end up being, or gal, would end up being about, I am assuming it's a 3/4, and it is. It's 3/4 inch, and these are standard sizes. And this one would probably be, I'm guessing, a 1/2 inch, because that's a standard size, and that's about a 1/2 inch. And then this really small one doesn't look that much smaller than the other one, but if you put it right next to it, you can see it is definitely smaller. Put that one on here. It's going to be just a tad bit smaller. I'm going to need to look at that one a little closer. It looks like it's in between our 1/2 inch and our, let's see, that would be 7/16. So that would be 15-30 seconds. All right, so it's about a 30-second less than the others. So here's our 5, and we should probably start making some kind of recording inscription so we can get our values on here. Let me start that right now. All right, as soon as I was putting this together, I instantly realized, look, working in fractions is going to be a real problem, an impediment to doing science. We're always going to want to use the metric. So I'm going to go back and I'm going to put the millimeters. I also knew I'm going to measure stability somehow. And I haven't figured that out yet, but I'm going to at least leave a block because that's what I'm measuring. So let's go ahead and get the number of millimeters for each of these. I can use my caliper again, and I'm going to switch glasses because it is really hard for me to read this small value. I'm going to put this on here. I'm going to use my right hand because that's what I'm used to, and get a pretty good value here. And these fractions, they're pretty close, but now I can read this, and this one, this large one, is 49. I can hold that up right here. You'll see that that 0 is going to end up being right before the 50. So this one is 49. I'm going to write that down before I forget. So this is 49. And that's going to end up being our millimeters. And then I can do the rest of these just as quick. I'll take this small one, put it up front here, make sure it just barely passes by, and that looks like it's about 25. So swing that around. Hopefully you can see that little 0 is on the 25. Write that right here. Let's get our next one down. Get this one. And I think I'm going to hold it, do it that way. Again, get it to go through the front of the jaw. And then I can squeeze it, and that is 19. And I hope you can see that 19 right there. Write that one down. And then the small one, the second of the smallest, let me put that one. And we said that's probably going to be a 1/2 inch, so that should be about 12 point something millimeters. So let's, that's going to be 12. And look, I can get an extra decimal on this. Let me see if I can hold this really steady. You get that jaw to barely go through. I'm going to, oh, I missed it again. I'm going to hold it here so I can squeeze this, so I can show everyone how to do this. Goes through, I'll squeeze this, and it's going to be right past 12, and this looks like it's 12 point So I'm going to put that, squeeze this right here. You'll notice that that 0 right here is going to be a little past the second line after the 10. And then we look at what line down below here lines up. And it looks like the number 7. 7 lines up with 40. Hopefully it's showing that. So we're going to be able to say that this one is 12.7 millimeters. And let's get our last one. This one's really small. Oh, wrong one. Put that through. Let's see what just barely gets through there. You know, a micrometer would be a little bit better here, but this will work good enough. Okay, that looks like, and that is exactly on 12. It's a little bit smaller, not by much, but 12.0. So I could put that right here. All right, so now I've got my number of millimeters, and now I can start to figure out what it is that we're going to use for stability. All right, let me get this set up. To help us measure stability, we need to think about what we can measure. First of all, I've got the 2 races of this bearing, and there's nothing inside right now. We want them to be identical. In other words, this bottom race should stay put, and the top race should follow identically. But as we saw in the videos, it didn't. You might have a little bit of movement. It might have gone one way or the other. And notice I've drawn 2 different configurations here. The red is indicating that that race is now off to the right side, and the blue would be off to the left side. That difference we could operationalize as our stability. Let me draw that out. So in other words, if I said, let's put an arrow from here to here, I could call that my delta distance. And I know that's a little bit small, but we could call that our stability. So green would be stability. So we want, for stability, we want our delta D to be as small as possible. Now, to measure this, we've got this dowel caliper. And this dowel caliper is used by mechanics to often find out if your brakes are out of round or something like that. Let me get this set up and I'll show you how this works. All right, I have the 2 races. I've got the largest spheres because I happen to have this set up at the right height. And you'll notice that I'm about at 60. Now what I'm going to do is I'm simply going to try to move this and see what kind of play that I have in there. And it appears that I might have like 5 one way and 5 the other. And so we would end up saying our delta D is about 10. And again, this one was fairly stable, but it had a little bit of movement, so it's kind of interesting. But maybe we'll use a rough value of like 8 or 7. I can always go back and look at the camera and see what it said. But let me get the next size set up. Okay, I have the 1 inch that are now on here, and we found out that the 2 inch gave us a value, we'll call it about a 10. And we'll call this our delta D, which we're calling stability. Let's see what we get on this one. And I got to get to the side so I can read it, so you can also see it on the camera. And whoa, I knocked it off. Much, much less. I'm probably getting a swing of maybe about 5 on that. So that one feels pretty stable. So we'll just give that a 5. And let me set up the next set. Take these off. Put these away. Lower this down a little bit. All right. Oh, that one feels very, very stable. So I got to push it in a little bit and just to get it to start to read. Okay, I'll put it at about, what is that, about a 60. And man, there is very, very little, let me get this on here. Very, very little slop in there. Probably 2 or 3. And I can feel it. If I push too hard, it just starts to break the whole thing off its rails. Let's put about 2 or 3. I'm going to say probably about a 2. And then I'll get the next one set up. Okay, let's do our 1/2 inch or the 12.7 millimeter. I have it on there. Looks like we're at about 75. And whoa, I get quite a swing here. Probably about 65 to 20. So that is a heck of a range. That's probably close to, we'll just call it about 50. That's a big swing. So I'll put that one up here. And then I'll get the last one set up. And it is a problem because I have to try to get this down pointing low enough to get to it. And I have to reconfigure this each and every time. Ready for our last run of 15. Oh, that looks terrible. Let me fix that real quick. Looks like my hand must have hit this or something. Or maybe I never finished it. But that should come all the way down here. I don't know if that makes it look better. Okay, that looks a little bit better. But regardless, I've got the smallest set of balls on this set of races. Now, I know it's got a lot of instability. I can see it. So I really have to preload this quite a bit. So I'm going to push this in, and I'll take it all the way to 0 right here. Roughly, I'm at an angle. I can't see it perfectly. But look, I can see this will go all the way from nearly 50 one way, maybe 60 one way. I can almost go all the way around. So that's probably like a swing of like 70 or 80. I'm just going to put 80. So this one clearly has lots of instability. I'll put 80 right here. And now what we can do is we can start to make a graph of this. This is kind of what we saw visually before. We saw that this one had quite a bit of freedom to move around, which we're calling stability. All right, let me start graphing this out. Okay, we formally have our data graphed, and I try to do it as accurately as possible. And so you'll see that at first I made large increments, and then I'd have those, and then I could put smaller increments in there, trying to get this as accurate as possible because, look, the 12 and the 12.7 are really, really close. 1925, 49, much easier to do. 80, and that might have even been a little bit higher, but we're going to call that 80. So here we've got our ball size down here, and we've got our stability, or our delta D, along the y-axis. And it goes up to 80. I put it up to 100. So we can see that it drops down precipitously, very, very quickly, almost like it's just aiming straight down. But then something unique happens here. This is not a typical curve that we get, where it comes flying down and then kind of levels off a little bit. There's got to be some physical mechanism for this. And that's really what we're after. It's one thing to collect data and one thing to be able to graph it. And I didn't bother showing how to graph this because I've done that in many other videos. But what's causing this? Can we form some kind of explanation that would tell us why we're seeing this pattern? And I think I have a pretty good idea. And I'm going to have to bring the camera in a little bit closer. But first, maybe I could draw it out, and then you'll see what I'm talking about. So let me draw this out. All right, here's my drawing, and here's what I'm trying to show. You'll notice whenever I'm using these spheres, they are going to end up having the ability to move in this groove right here. And that's what I'm trying to draw here. Imagine this being the groove in that race. If I have a ball that is smaller in radius than that groove, it can move back and forth. But let's say that we had a much larger ball, and I'll draw that now. So this is one groove on one side of the race. This would be the groove on the other side of the race. Imagine if we had a ball that was way bigger. Well, something like this, you'll see that instead of only touching at one spot, it touches here and here. It's got 2 points of stability. See, this ball technically is only touching at one spot on the bottom, and therefore it can roll up the ramp to the other side. But when you have a ball, and if these are the bearings here, okay, this one can't roll, and that's why it has so much stability. So I am thinking that somewhere in this range, we end up matching the curvature of this bearing. And once we get a little bit larger, then we are hitting at least 2 points. And that's what's probably giving us our stability and helping us explain at least this part of the curve. Why it gets a little bit less stable as we get bigger, well, I think that's going to end up being a ratio thing also. But I have an interesting way that I think that we might be able to test this. In other words, if I took this bearing to the edge and I let it go, I could count how many times it's going to roll back and forth. That might be another way to talk about the predicted stability that we might get using the various sizes. So now I'm going to bring the camera so you can see this closer, and maybe we'll do that. I've already got this. Maybe I'll just put one more column here for the number of oscillations it makes. All right, I've got the race right here, and I think I can count the number of oscillations, and I'll let it go, and 1, 2, 3, 4. Oh, that's going to be hard. I think I'm going to put it closer and put this camera on slow-mo, and that'll help me count the number of oscillations. All right, that slow motion was a big help. Not perfect, I only did one run, and this very smallest ball ended up sticking to your fingers when you'd let it go. You almost had to push it or lower it down into the groove a little bit before it would start to move. So I have a feeling that one might even be a little bit low, but regardless, we can see same general pattern. We might as well graph this also. Now, I already have green for my delta D, which we're calling stability, and I'm just calling this rolls, number of rolls back and forth. So sometimes you don't have enough space, and I want to get everything in one shot here. So here's what you can do. You can just add another y-axis, and a lot of people don't know that you can do this, so let's do it and show you how. Now, I only need to go up to, we'll say 50 instead of 100, so I'm just going to take and make another y-axis right here, and I'll go up to here, straight down, and then I'll put little marks, and this would be 10, 20, 30, 40, and 50, and then I'll put this as rolls. And then I can just plot these points. So for my smallest, I'm at 39 and then 34. So I'll just find these 39, so which would be about right here, I think. So 39. Oh, I think that's above my 40. It's hard for me to see. So I'll try this right next to it here. fringing on that green a little bit. And then the next one was 34, so this one would be 34-ish, about here-ish. And then we're all the way down to 4, and if that's 10, and that would be 5, so that's probably about 4 there. And then the next one's up to 12. 12 for us would be something like this. And then we're all the way back up to 35. So all the way at 35, something like this. So in this case, we can see that maybe we have, oh, I missed this bottom one. Maybe we have a similar pattern again. We come down, and then this one is maybe a little bit more of a V shape. Regardless, I think we have done something really productive here. We've come up with an explanation. It's real easy to just collect data, but if you can start to say, no, there's a reason for this, and in this case, it just happens to be geometry, as if that's a new one, because geometry is usually the answer to all problems. So we now know that it's the fit of the radii into the groove here that really makes a difference on the bearing. So this is pretty good. All right. Again, we're working on these long terms, and eventually we'll put this together. This is part 4, making progress. I think this one was a real win. All right. That's your quiz, and that's our long term as we're moving along. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.